And welcome to this video. This is for Itumalain, and this is the March 2021 paper. Obviously, it's paper 42, and this is question 7F. And here we go. This is 7F. All right, so we've got a weak acid. ACEs is a compound that can be used to make a buffer solution for electrophoresis. There it is. The anion is that, which is a strong base. Okay, so that means it's going to react totally when we dissociate it. All right, a buffer solution is prepared using this. So we get 3.5 grams of the base. Okay, not this, the base. And we dissolve it in 100 cc's of water. And then we add sulfuric acid, HCl to that. And then the resulting mixture is transferred to a 250 volumetric flask. And we make the solution up to the mark. We get a 1-to-1 reaction. And the pKa of ACEs is 6.88. We've got to find out the pH of the buffer solution that's formed. Okay, so let me do this. I'm going to call, oh no, let's do it properly. So C4H9N2O4SNA is going to react with HCl. And obviously, it's going to reprotonate it, isn't it? So I'm going to call this C4H9 N2O4SH. All right. And it's going to reprotonate, and then we're going to get NaCl left over. So, and it says it's 1-to-1. So there you go. We've got all the components we need. Okay, so let's do some figuring it out. All right, so the number of moles of the original base, this stuff here, is going to be 3.5 divided by 204.1 because they've given us the relative atomic mass. I've worked this out earlier and it's 0.0171. So we start off with this. HCl, number of moles of HCl we start with, is 50 times 10 to the minus 3 times 0.2. I worked that out earlier. It's 0.01. So there you go. So as you can immediately see, the base is in excess and the acid is the limiting reagent here. So how much of this will I get? The original acid, I'll get 0.01 and 0.01 of this will be used. So we'll end up with 0.0071. Okay. Now, I know maybe you don't see this, but if you look at this the other way round, let me get a different color. This now becomes C4H9 N2O4SH. This stuff is in equilibrium with let me get rid of that bit. There, C4H9N2O4S minus H plus. It's the reverse of this. If you look at it like that, it's going that way, isn't it? This is how we normally write it. This is the acid dissociating to the base form, and there's hydrogen ions. So if we fiddle around with this one, we get Ka. It's going to be the base form, this stuff, times the H plus, divided by the acid form, which is this stuff. Fiddling around with it and using the the pKa is 6.88, we get this. Let me see if I can figure this out. We need H plus. We want the concentration of hydrogen ions. So that's going to be Ka times the concentration of the acid divided by the concentration of the base. I'm just rearranging this equation. And let me put numbers in now. Now, Ka, well, this is pKa. So Ka is 10 to the minus 6.88 times the acid concentration, which is this, 0.01, which is this. Okay, divided by the base concentration. The base concentration is this. Well, actually, I'm not using the concentration, am I? I'm using the number of moles here. Now, the reason I can do that is because they're all in the same volume. The volume term will cancel out. So I actually don't need that 250. Okay, so that's the H plus concentration. Let me use a calculator. I've done this already, but obviously I've deleted it. So it's 10 to the power of minus 6.88 times 0.01 equals that. Divide that. Oops, I've done that wrong. Sorry about this. Let me do that again. 10 to the power of minus 6.88 equals that, times 0.01 equals that, divide that by 0.0071 equals that, and I get the concentration, H plus concentration, is 1.86. I'll say times 10 to the minus 7. Get the log of that, and I get the log of that is 6.73. Okay, hope that makes sense. Let me post this now. Okay, bye-bye.